Hello, everybody. Um, Today we will talk about Simulink. Now, Simulink is a toolbox, a software provided by Matlab that simplifies the design of systems, simulations, and basically everything in Matlab because you don't have to know any programming. You have some visual components that you can drag and drop, and you can connect them, um, and you can just achieve what you're trying to do. So you can basically create nice simulations. And of course, it's not that difficult to learn Simulink, considering this fact. Therefore, I will quickly show you the components that are mostly used by us, and then I will transition into some advanced cases, some advanced methods to utilize Simulink to improve efficiency with Simulink. Now, most of the time, you already have used Simulink for this is highly probable, but it is also the case. It might be also the case that you didn't even touch Simulink. So basically, if you type in Simulink here, I did type Simulink here. Where is it? If you type in Simulink here, you will see that this pops up because I did open it. It loaded the screen. If you want to open Simulink, you can just type in Simulink in the command window. Or you can use the graphical user interface. Here somewhere should be a Simulink button, but you might have to search for that. I don't really remember where it is. So basically, there you go. You have the Simulink button here, but I prefer to type in Simulink, and it's up to you. Now, you can see that there are many options here, and not all are necessary for you. So I'm just skip that and click here on a blank model, so I can create a nice new Simulink model here. It takes quite some time, and after that it opens up a window where you have nothing available here. Now, if you're using the latest versions, then this is not a big problem, because if you type something, let's say step, you will immediately see that Simulink provides you with a list of available components that are named step. And also, you can just click this library browser here, and you will see that it takes a little bit of time, but after that it will provide you with a new window. And in this window, we will be it will be possible to choose the components that are necessary for our model. Now, you can see that it is trying hard to show me the window. This happens when you never use this Simulink and the library browser. Then it needs a little bit time to load, because it has too many toolboxes here, and it is trying to load all of them. Once you've done that, you can click and you can see that it pops right away. So that's that. Now, there's also a nice option here. You can see that commonly used blocks are given here. So you can just go ahead and let's say drag and drop, as I've mentioned. And once it is done, it will show you a constant. So you can just drag and drop, and these representations will be on this working area here. And there are quite some components, and they are very useful if you think about it. You can see that we can provide a constant. We can also have an integrator here, let's say that. And then we can have different options. Logical operator, saturation, scope. Maybe a scope is a good idea. Now, once you have selected your components, you're just aligning them, and Matlab or even Simulink just connects them, or shows you how to connect them, or it adjusts the spacing. So once you're done with that, you can just go ahead and run this model, because I have already connected everything, and I have a constant block, an integrator, and a scope here. So once I run it, I will see that it will build the model. So it's backing up, building, compiling, and whatever is needed for that, and it is done. So it did a 10-second simulation, and if I double click the scope here, hopefully it should pop up a new window that will show me the result here. And you can see that I have a ramp function here. Now this makes sense because I have provided a constant to an integrator. This means that the integrator will add this forever. So it's taking the integral of the constant, which is time dependent, and it's t, by the way. So it is one here. So here we have a ramp function, a unit ramp function, basically. So it will write like this. If I want to, let's say, change anything, if I want to change the constant, I can just double click it, and it will show me a window where I'm able to manipulate the value, and I can also change the integrator properties. It might have some limited outputs, it might have some initial conditions, and it changes. Every component has its own unique properties, so you might want to check it out by double clicking on the components you are using. Now basically I've changed the slope here. In 10 seconds it reached the value of 20, which means that I have uh, a, a slope of 2. So this is basically that. Now most of the time the scopes are uh, like this, with black background and some um, weird color for the plots. The reason behind that is that it kind of emulates an oscilloscope, or some derivations of oscilloscopes. So it kind of aims to give you the feeling of a laboratory environment. So that's why we have these different color choices. And most of the time, you might want to get rid of it if you're especially using a projector, if you're going to have a presentation and you are including any graph from these scopes or Simulink, then it might be a good idea to change the style of this, and I will quickly show you. The reason behind that is that projectors mostly use light to render this image, and if there's something black, it means that it will just turn off those pixels, and if that's the case, it might be very hard to see the projection, or the projected version may struggle to show this line exactly, or it might be not readable. So it is a good idea to have a white background, because it will not turn off the pixels that are not there, or that aren't white. It will project, and if you have a nice color, it will be a better projection. A projected image will have a better quality. So it is important if you are trying to prepare a presentation. Now, as far as I'm concerned, if you change this to white, you can see now we have kind of the axis color should maybe be black in order to not the axis. I'm sorry. This color here should be black, so you can see that these lines become more visible. And then it can be automatically like that. I don't know. But the line width, as always, should be something like this. Maybe it should render red, and then apply this, and you can see that this is a much better graphic in terms of projection, for presentations, for projection. Uh, but the other one has the advantage of being easy on the eye. But as I said before, the purpose of your graphics is very important here. Now, it might be the case that I want to show the input and output on a single graph. Now there are two methods to that. You can go ahead and right click this scope here, and you should see in the properties that we have something like whatever then signals and ports, and you can change the number of input ports. That's one way of doing it. You can just click that and you will have two inputs here. But I don't like that method. Most of the time I use something called the MUX or DMUX here, a multiplexer basically. And I will tell you why I'm most of the time using this. Now I am adding this here, and then I copy and see what that is. From these styles, I might want to change. Um, this is one here, so this is red. Maybe before I do that, I have to run this model. Now, if I go to View Style, it should show me a second. It doesn't show me a second. Okay. Now, for scopes, it might be not a good idea to choose the MUX, but because I'm also not using Simulink for some outputs, I will show you in a minute why I'm going to prefer MUX over the usual method. Let's change it. Copy. Let's change the single ports. Um, let's say this is the output and this is the input. Now you have to run the model first in order to be able to change the appearance here. Now, okay, it was here, but I didn't see it. So let's make this red, and let's make the constant black. So I can see now, and I can visualize now that I have a input that is black, and I have an output that is red, and the relation between the input and output is given here. So I can basically use this here. Now, there are also other things. We might want to use some, let's say, transfer functions. And we can see that we have an integrator, we have a PID controller, we have a state space representation, or a transfer function. Now, if I want to use a transfer function instead of this, I might want to show you the difference between an integrator and a stable first order system here. Now, if I run this and click here, let's see, you can now see that I have an input reference of 2, and my first order system has a certain settling time to it and doesn't overshoot and um, tracks the reference. Now, it is also possible to construct some feedback loops. Therefore, I need a sum here. Let's take a sum. And by double clicking it, I can go ahead and change the signs of this. So it should be plus and minus, and this is my reference. Therefore, I might want to use this as an input here. Let's get rid of this and just drag this over here. Now then, I have the system here. I disconnect there, and then I have this feedback here in feedback loop. So it's very easy to construct control systems, as you can see. I'm just dragging, dropping, and connecting stuff. So once it is done, I can see now that my reference is 2 and my gain is overall 1 divided by 2 because the output is settles down to 1. So this means that if I have a reference of 1, you can easily see the effect. And you have a run button on the figure here, on the scope here too, so it's also possible to use that. So basically, in order to adjust this, I might want to use a filter, a pre-filter here, in order to change the gain here. And therefore, I will just go ahead and type gain here, so you can have an element, a gain element here. Dragging, dropping, again connecting everything. And I know that my system needs a gain of 2 from the input. And I will mention a little thing that is very important in terms of gains or filters that might be used by us. So basically, this gain should be included into the system, which means that my input reference is now 1 and not 2. So this should be embedded into the system. Now you can see I have this effect here where the settling time is a little bit decreased, which means that the system became faster. Now, the important thing here with the gain is that I might change the gain using the input pre-filter here. But it's not possible to change the gain using the output, and by that I mean the following. By the way, you can select a rectangle. You can select a rectangle here, copy it and paste it, and align them, and there you go. You have another loop, another feedback loop here. The only thing that I'm going to change here is I'm going to use the gain at the output of the system. Now, this might be this might seem correct to you because it will give the same result. I will see the same output here if I run it. I can see that this is the same thing here. If I change it to 1 and then if I run it, I see that this gain is pretty much necessary to adjust the gain so that there is reference tracking, but there is a big difference between these two. And there we go. Even though the outputs are the same, and even if it seems correct to you, the second one makes no sense, or is a little bit problematic, because the output is a quantity or a signal in the real world application that you cannot change, because the output is the output. So if you have a room temperature control system and you have an output, that means that you see a 10 degrees Celsius output of the system, or the control system temperature in your room. It seems to be 10 degrees. If you multiply that with 2, that means that you are just interpreting it as 20. So that's not what in real life, or what the actual value of the room temperature is. You're just multiplying that by 2 and just assume that it is 20 degrees. It is an interpretation of the output, not the output itself. But what you can do is you can apply twice as much control input that is used for the previous output. Since this is a linear system, then your output will be twice the amount of the first design. Then you have a different case that's corresponding to the first case. So what I mean by that is you can adjust the input, or you can use pre-filters using the input of any control system, but you should never ever go ahead and connect a gain or a filter, a post filter in this case, to the output. Because let's think of a plane that is losing height, which is practically falling down, and you're going to die in 10 seconds. So in this scenario, it is available to, let's say, multiply the output with -1, which means that you're gaining height. And this is just an interpretation, because that's not what's happening now. If the plane falls, if the output is negative, then you have something negative. It's not possible to multiply that with a negative value in order to get a positive output. So you should never ever go ahead and touch the output of any system, or of any control system. You might want to change your reference, because it is also obvious that if you want to have twice the amount in the output, you should provide twice the amount of input you have applied before. So changing the input is the only sensible thing to do here. That's it. Now let's focus on Simulink again. And you can see that you can choose some controllers. You might want to have a integrator in your controller. But in the case of a P controller, which we had last lesson, we can just go ahead and choose the gain here, since that's the easiest controller, and since that's the controller from the last lectures, we might want to change this. And I can see that I can speed up the system like this. By the way, I should maybe go ahead and use the first model, not the second one, because the second one is not correct at all. Let's connect this here. There we go. Let's delete the second one. So you can copy, paste, delete. And if you hit space, you will see that it will align nicely. It will zoom in so that it fits exactly. If you hit run, now you can see that our gain is not appropriate for this system. If I don't have any gain, I can just go ahead and click that, and I can see that I have a certain value here. And for that value, I might also want to use now a display. So you can just type in display, which will be a numerical screen here, display basically. So, and you can go ahead and connect it to any signal you want to see. And keep in mind that this will always give the value that is available at the time instant. And once your simulation is finished, you will have the final value of that signal. And you can see that. Observe this screen here. You have suddenly 0.66. If I increase the stop time, so basically the simulation time, it's also not possible because it is too fast. It's calculating it too fast. So I might want to change that in a bit, but I can see that my steady state value is 0.66, which means that it is 2 divided by 3. So if I use a gain of 3 divided by 2 or 1.5, I can just go ahead. By the way, you can leave it like that and Simulink will use it. And you can see that it is practically 0.9999, which is approximately 1, but not exactly 1. And if you've listened to the last lecture, you know that the p-type controller has always a steady state error. And it is, by the way, also almost possible to correct it perfectly, almost perfectly, basically, by using a pre-filter here. You look for the closed loop system here, which is 2 divided by s plus 1 in the feedback structure, which should give you basically 2 divided by s plus 3, if you go ahead and calculate it. So 2 divided by s plus 3, plugging in and using the final value theorem, you can see that it is 2 divided by 3. By using the inverse of that gain as a DC gain for your reference, or as a pre-filter for your reference, you can get almost 1, because there is a division error, numerical errors. You have 0.9999, which is kind of usable, but we will see in a second if we have a different case, it might be a problem. So let's say I have disturbance, and I've talked about this, and let's say we have a constant disturbance, but this disturbance is not always available. It will be available at a starting from a certain time instant. In that case, I might want to use the step function, which can be used for this purpose. And I also need a sum here. That means that I have additive disturbance in this case. And most of the time for these systems, I don't like to use this here. You might want to change it around. You can flip it. You can rotate it basically. Let's try to flip it. Flip the block here. You can see that you can go ahead and flip it. Let's flip it again to have the original one here. I didn't want to do that. So if I flip this again, flip the block, you can see I have this here. You can also rotate it, but you might want to double click and change the shape here, rectangular, and just get rid of everything and put in two pluses. Here you can see now I have a different visualization here. Now, if I want to add this to the output of the system, I might want to do something like this here. So you can see now I have a certain input here, and I might want to connect this one here. And let's select everything here. As far as I remember, we can change something about this. Never mind. Okay. Now I have a step value. Let's do not have a big value. Let's say 0.2, and uh, that's basically the step time. That's not what I wanted. The step time should be, since we have 10 seconds, and I will adjust that back. Let's say in 5 seconds. If the time hits 5 seconds, it will apply this value, and the value should be 0.2. And let's have a 10-second simulation here. I'm not going to save it for now. Now let's hit run. And you can see that there is a difference basically. You can see that at this point I have a 0.2 disturbance, and keep in mind that this is the output. The output is rendered in red. So this advantage of a PI controller, of a P controller, I'm sorry, is that it cannot compensate for disturbances, because it is not, it's just using the value of the error, and the error is not going to be zero in this case. And it's not possible to change the output anymore, since this is just a static controller. Now, if you want to compare this with a PI controller, let's say, let's copy this, paste this, and basically place it like this. You might want to get rid of this. If you want to apply the same, you might just go ahead and connect it to this line here, and you might also want to use the same reference. The reason why I'm changing this way is that I want to use this reference and this disturbance, and if I play around, it should also affect the second model that I'm trying to compare here. Let's have this gain, and let's add also an integrator, or maybe we should add a transfer function. So basically I should copy this, paste this, and let's come up with an integrated control. Hopefully it will be, I'm sorry, it should be 0. Okay, now you can see that this is a PI controller. Since I have that, I don't need the gain anymore. I can just plug this in here. I might want to make it like this. There we go. This should be a PI controller, since it is cancelling out s plus 1 here. It should be 1 divided by s, and if you think about it, it is 1 divided by s plus 1, which is basically an ideal design here. So I don't even need this gain here, because I can just apply that input here, and this is my reference, and I will see the difference. And keep in mind that I have this disturbance still affecting both the models in the top and the bottom here, and I have these two. Let's hit run here. You can see that there is a big difference in terms of disturbance here. So I have now visualized and compared two controllers. I can also plot them on top of each other, but I can see that the integrator effects here, it takes effect at this point where the P-type controller stops reducing its output. The integrator is still taking the sum, and there is still a difference, and it tries to compensate for that fact. Maybe it takes a little time, but there's a settling time to the system, so it also will take a certain time for this. If I want to speed this up, I might just go ahead and change the overall coefficients. So maybe let's say 4, 4 should give a 4 gain. And if I have this, I predict that it should be 4 divided by s plus 4 for the closed loop system. Now I can see the exact value here, and I can also see that my second time become less, and I have a much faster and better system overall. Now it is also possible to use this here and flip it. If you know the shortcuts, it might become very helpful. And it is also possible to maybe, should I do it like this? Maybe I should manipulate the output, so I'm taking it back. Well, let's do not take it back again. Let's take this here, connect it here, hopefully, and connect this to here. And I have to apply a noise. So for noise, you can just use a bandwidth limited white noise, which is basically the model used for noise, and maybe a little gain can be. There's some noise forward sample time and C. Do I have gain? I don't know. Let's apply this here. Okay, and I need the same thing here. Because I want the same noise, I will connect it like this here. So I will use the same again, and this comes from here, and I will connect it here. So if I run this, I can also see now that I have a very bad signal here, and I can also see here that there is a bad signal. So basically I need a little gain. It's too much. So I did apply a little bit too much bandwidth now. By the way, if you change the game, many things change about this, but I want to, or maybe I should mess up with this. Let's reduce the noise power, let's say. That might be helpful too. So as I've mentioned before, every block in Simulink has a very different usage. It has some properties, so it's still too much, I guess. It is a coincidence that my maybe a golf noise would be better. Not sure at this moment. Let's see. Is it still okay? It is a little bit better now. I did reduce that. Since there is always noise, it tries to keep it like that. But if I, let's say, have a greater gain value and try to stabilize the system, I will see that the performance gets worse, and I'm not even tracking the place there. And I've talked about this in the last lecture, and I've said that having a greater gain value means that I will also multiply my noise here. And since noise is something that is of high frequency and unwanted, I'm increasing the effect of this. But as you would remember, if I do not have any noise and disturbance, this would have caused the system to track a better output or have some better tracking properties here. Now, if I do not have this, maybe we should use a gain data for that. If I want to, there's also some other structures or components that can be useful to switch off stuff here, but using a zero gain is the best and quickest way for disabling noise. And I might also use this here and paste it, Control I, and then go ahead and use this as a gain for my step function here. Now they will together build my system here. Now if I want to disable both effects of noise and disturbance, I can see now that I need to change this basically. If this is 10, it should give me a 10 divided by s plus 1. Let's also get rid of this here. Let's say this is 1. Because it will not need that much of a a pre-filter here, and you can see it is 0.9, but if I have a less gain value, let's say 2, it will not be 0.9, it will be a lesser value here. So having not, a high gain is most of the time a good idea for the p-type controller to have less steady state error. And if you have 100 basically, or 50, let's say 50, it should basically almost vanish. It means that 2%, which is basically the definition of settling time. So if it's like this, we can assume this uh, as settling time, but you will see that having an effect with the disturbance will be a problem on its own. There is a peak, but since I have still high gain, it will use more of the error, so it will have a stronger um, and disturbance rejection here. But if I have noise, and that's the biggest problem here, I will have some problems with compensating the noise, and you can see that the original noise signal is amplified too much here. It's 100 times, and if you remember, I have changed the power of the noise, and if you increase the power of the noise, which might be the case, you have to use frequency domain analysis for that, and it will become worse and worse. Since high gain will amplify the noise too. This is, by the way, measurement noise, and that's inevitable in the real world applications because there will always be a measurement noise, even if you use some filters like Kalman filter or other band stopping or low pass filters. You will have this measurement noise, and this measurement noise is not inevitable here. But my PI controller still tries to track the output, and you will see that it will try forever because there is a dynamic component in the controller, namely the integrator, which causes this reaction and which can be used as memory. And I've talked about memory. So the integrator looks for the memory that starts from zero here, from time instance zero. So it will always try to compensate for noise and disturbance. So basically, the p-type controller is also not that much used in most cases, and I've talked about this. So that's basically it. Now you can see that there are many things here. You have zero pull, you have zero delay. You should go ahead and check it out. This is not that much useful for us. Discontinuities, maybe you want to use a dynamic saturation or just saturation and saturate your signals, limit your signals because in real life applications there are such needs. Discrete time toolbox, there are now toolboxes, lookup tables, math operations. You should just go ahead and check it out. If you have a design or an algorithm to implement, you might also want to use these blocks here. You want and the ease here comes from the fact that Simulink is basically a for loop on its own. So it loops through all time instances and uses every value at the time instant that's available. So you are basically bypassing the usage of arrays here. If you have something like 50 here, it will be applied to every element of that array. And basically, if we would have used code here, we would have defined this as an array, this would be an array, this single would have been an array. Everything would be defined as an array, but since we are using Simulink and drag and dropping stuff here, basically everything will be used as an element at the time instant that is the index of the array that's corresponding to that. But it is very easy to use this version where you drag and drop stuff and do not cope with the arrays. So basically, it has some advantages. That's also the reason why you are prototyping in Matlab and basically in Simulink, and especially in Simulink, because it is a fast prototyping toolbox that helps you. most of the time. But keep in mind that once you have decided and verified your design, the process of converting this into code is basically necessary and will be the next task there. So knowing code is also important. And this has also some disadvantages. I will come to that in a moment here. Model verification. There are plenty of stuff here. Now, for the usage of some things, you can basically embed some functions and do some other stuff. I'll hopefully show that too. Now, signal routing and mux, the mux is here. You can have a manual switch if you have two choices. This switch might be a good idea. But it is also a good idea sometimes to use these labels here, from to and go tos. And I will show you the usage of this. Let's get rid of this signal connection here, because in Simulink sometimes it becomes a bit messy. Now I will use this here, and I will give it a name, a tag basically, and this tag will have some visibility. I might use it as global, and I might call it disturbance. If I apply and hit OK, now I have disturbance here, and I might want to change that. So I can just drag this on top of, on the left top corner, and wherever I need to use some disturbance, I might want to connect this here and give it the tag now. There's also a list here. You don't have to remember everything, and you can use this here. Now I have basically connected my disturbance to this model. I can also create a copy here of this tag and go ahead and connect it here. So this way you can also use this constant here and the gain here. Maybe not the gain is not important anymore. And let's copy this and paste this, and let's connect this here and change the name to reference, the tag to reference. Let's say ref. That's So keep in mind, having it global is a good idea if you have multiple blocks, but you can also use it locally. You have to toy around with this a little bit. So there's an arrow here that will generate the from and go to text from each other, so you can use that basically. There's another arrow for that. Now I will get rid of this and this connection here and this connection, and I will just go ahead and connect this here. I might also want to copy this and connect it here. Now basically I will do the same for noise. Let's copy it here, and let's again use this here, paste it, invert it, and connect it here, and call this noise. So now this is noise, and I can also do this here. Change the appearance, and then I'm going to copy it and paste it here. So there we go. Now there are no connections between these, and it is a little bit better. You can also arrange them so that they are on the left, and then also drag this down here. And if you hit space, you have a nice tidied up version of the same simulation, because at some point in Simulink you might have some issues considering the connections and keeping track of the connections. That can be a pain, but using these tags it's possible to solve it, and you can see that you have basically the same. And since I want to plot stuff, I might want to use something like these tags also can be used here, but I'm not going to use that, and I will also not use this scope here, maybe the display can stay here, but I'll not use the scope, and I will show you something that might be important for preparing reports or stuff. Now, basically, I told you, let's get rid of this too. Now, let's say I want to save this to a mat file in order to use it later or use it using the code. It is possible, and I can use the mux element here in order to create just one signal that has many dimensions. And I might want to keep track of disturbance, reference, noise, and all the resulting signals here. Now, there are many choices, but let's say we want to use the reference, the disturbance, the noise, reference, disturbance, noise, and the output itself. Mm, So these are basically four elements, so I should use four inputs here. Let's connect this reference first. We will have the reference connected, and then I might also want to look for the disturbance. Let's connect this too. Let's make it maybe smaller, maybe like this. And then I have also noise. Let's have noise, and let's invert it, and let's connect it there. And I want to have the output. Now I can basically connect the output here. That makes sense at that point. And let's say I want to save it to the workspace. I can use two workspace here, and that will save it to the workspace. I can also save it as mat file. So basically, it's possible to use that. Maybe to file can be a better idea. So let's call this something different than untitled mat, and let's call it uh, controller P, something like this, and maybe a capital C will look better. And the variable name should be, what should we call it? Let's say data. That looks. And now there's also an option that you can use the time series or array. I'm going to use array and some decimation, etc. But I will not be considering these. Now I have this controller P now. So this means that if I run this, I will have a file generated. By the way, let's save this also here. Let's say model.slx. I will save this. So this shows that in Simulink you don't have to save in order to try stuff out. Now you can see there are things, and I have used the. You might want to use the workspace. I have used this to file here. Maybe you want to use display. By the way, you can stop the simulation using this. This might be a good idea. You might want to use a mechanism that checks if there's, let's say, you are dividing two signals. Let's say there is a zero division, so you might want to inspect that and get, or you might want to use the stop simulation if there's a zero in the signal and you can prevent stuff from crashing. Now, there are sources, and I've shown you there are some band limited noise, some counters, ramp functions, signal generator, which has some properties on its own, random numbers. There are also, interestingly, some string manipulations. Maybe you are trying to simulate a TCP/IP system and you have a message you want to do some crazy stuff on that. You can do that too. There are user-defined functions which might become very important for applications that are really complicated and firmware. There are some useful stuff here. You can use Matlab functions, systems, functions, and C functions even. Therefore, you have to set up next. If you have done that, you can use C functions. Now, this is a nice addition if you think about the slowness of Matlab or sometimes you have some algorithms in C that are very, let's say, speed dependent. Then you might want to code that part in C and use a MATLAB for your simulations, which is very nice. You might want to create let's say, basic C function that uses some data coming from a server, and you can implement TCP/IP using a C function. You might want to use that here, so you can extend your model as you wish, basically. And some other toolboxes that are not that important for me at the moment. You can go ahead and check this library browser out. Now, if I run this, and I have this workspace here, or let's say we have this here, I have saved my model, and if I run this, you can pay attention to here. It just basically generated my controller p.net. Now, in the command window, let's call the editor here, and let's go ahead and clear CSV. Now you can double click that in order to load it to the workspace, but I will not do that. I will go ahead and say load, and then give it the controller p.net here. Now you can say something like this: data equals load, or temporary equals load. So it will save all the data into a variable here. Now I can see that I have a structure here in there, and it shows me that the structure has data in it. So maybe I should extract the data using temp.data, and then I will see what data looks like. Now you can basically see at this point we have an array, and this array has some signals in it, and the values of the signals are column-wise. So basically, I should remember, or I should look at my model and extract the data looking at it, and I can do that by the following code. I can extract the data. I can define something like reference and say I need the first row and all columns. So basically, now I will have the disturbance. I will have noise. You have to pay attention to the order here, and this is why, because this is the output. This is the second row, third row, and fourth row. Then I'm also able to create a figure. Hold on, plot t. So basically, there is one more to it. If I count here, 1, 2, 3, 4, 5. And as far as I remember, hope I'm not wrong, the first data here is the time data. So basically, I will call it t, and I will see that this is the first row. If you change it to the data type to array using this to workspace or to file block. If you do not do that, you will have a structure that will contain time data and all the data separately. You might want to prefer, you might want to use that, or you might prefer that one. It depends. So line width of 2, let's give it a display name. So basically what I'm doing here is I'm generating the report or the result using MATLAB code, and this is most of the time a better idea. If you have a complicated simulation or a simulation that will have some multiple runs with it, it might be a good idea to change it so that you can adapt to most of the situations. And this is what I'm trying to do here. If I, let's say, plot the disturbance, the noise, and everything, it is basically possible to use the code to do stuff for you and not the Simulink scope, because the Simulink scope is not that flexible. But here I can change stuff around and run the simulation, and I will hopefully, if I have enough time, show you also how to use some MATLAB code running the simulation. So the X label is time, the Y label is, let's say, YT, and then I will have the title, And then the jam show, and you can immediately see the results here. Now there is a little problem because it's not distance, it is disturbance. Somehow I didn't uh, do the right thing. Now you can see that maybe grid on would be a good idea to have a nice grid in order to compare stuff. Now, not all of them are references. Maybe this is disturbance. Let's call it PT, and let's call this NT, which is noise, and then this is YT. So maybe we should call this RT, which represents the reference here. Well, basically, I can see now that I have a an interesting output. This is my disturbance. This is my basic noise here, and this is the output generated by the system. Now, since I have done the P controller type, maybe it is also possible to extend this by just copying and pasting. And let's take this here, maybe this here, and use this. Let's say controller PI, or maybe data 2. Is it possible? I don't remember. Maybe we should use that there. Um, okay, it should be different files. Okay, then I will create this, and it is again called data, and it is again an array. So at this point, I will just go ahead and load the other data here. So this is data. Maybe I will, once I'm finished with this, let's do it like this here. So this here, and this is data. T is again this, reference to, disturbance to, noise to, and Y to, in order to compare everything. So I might want to get rid of this reference, disturbance and noise, because they are the same. I know that for a fact. Now maybe I might also plot the other output, which is Y2 and T2. Let's make it T2. Let's make it like this. And let's say PI, and this one is the P-type controller. And we have an error because we didn't run the file. So there's nothing called controller PI mat. So let's save it, let's run it. So let's run this one here. And you can immediately see the effect of the integrator. We do not have a rise time that is crazy like this purple one, which is a P-type controller, but we have a more reasonable design. We can see that this one takes effect here, and it just has a better disturbance rejection and noise attenuation here. So having complex structures is easier with Simulink, but using Simulink via code or with along with the code is a even better idea, because you might want to automate stuff, or you might want to keep track of everything a little bit better. Now there are also helpful stuff like drawing a box here. You can just go ahead and create an area here and give it different, let's say, colors and stuff. I did copy it by control, but it copies also the internals, so that's not a good idea. Let's draw another one here. Let's give it a different color. It's all customizable here. I might want to use this here. I should have been able to change the area properties. There are no. Area color, there we go. Then you can change it to a certain amount, let's say yellow. Now you have you can also type in, as far as I remember, So this is the P-type controller, and then you might also want to have a PI type controller. Now this is a good idea here because most of the time it is possible to use this. Now basically it is also possible to select certain blocks here, and you can create a subsystem here. So maybe I want to call this subsystem uh, signals of the system. If I double click it, I can see that nothing changed basically because this doesn't use the inputs and outputs. It is just a block on its own, so you can just go ahead and place it like that. I might also want to use a component that has inputs and outputs and create a subsystem out of that, and I might call it the controller here. So if I double click it, now I have inputs and outputs and I can name them. And the name here is error, and it will generate me the control signal. And this is basically the controller structure. I might also want to go ahead and was it this one? This one was the controller. I might want to also define this as a new system. And if I go ahead and click it here, this is called the error, this is called the control signal, and this is now the PI controller. I can basically create some subsystems, and it might be, let's say, controller PI, controller P. So they should have basically different names. And now you can see that I have a nice, clean way of designing controllers or comparing controllers, and I'm saving them to their individual mat files, and everything is very simple structured and manageable in this case. Because I know that at some point there are too many integrators, games, and then too many lines connecting stuff to each other, and it becomes almost unmanageable. And we tend to copy and paste most of the stuff, and it names them, it gives them silly names like controller 1, controller 3, controller 50, and then you are trying to get it working, but you might forget about something, and it's not really easy to see and debug that whole model. So using subsystems, some areas, and these labels is a better idea here. Now, let us create another model. This time, I can see that I can create a blank model. There are also subsystem state charts. Whatever you want, you can almost generate and create everything here. And we have a blank model here. Now, I am going to basically copy everything here. As you can see, I've copied and pasted stuff. Now, let's close this. Let's close this figure here. Now here, I will call it model 2. And then instead of 2 files, I will create a 2 workspace. And I will basically connect that. Let's look for that as an array. Well, maybe let me show you the structure with time. Could be a good idea. Or time series. Let's try the time series one. Let's apply that. And let's hit OK. Now, basically, what I'm going to try to do is I'm going to try to use the code basically in order to generate everything here. Now, let's get rid of the disturbance. Let's get rid of these labels here. Um, for the moment, I will have the simplest version possible here in order to demonstrate stuff, and then you can extend the whole idea as you wish. So now there's also something called from the workspace, as far as I know. Yeah, here we go. Now you have to generate this so that it has the appropriate values and data in it. So if we will use the time series, it should have some properties like this. If we use matrix, each row of the matrix has timestamp in the first column and a vector containing corresponding data in the subsequent columns, which means that maybe it is a good idea to use the array here. So is there something like in? Okay. So since I'm using a mux for output, I will also use a demux system component basically that will separate the array so that I will use it basically for my purposes here. Let's get rid of the gain here. I'll just directly connect that. So maybe I should drag them here. So let's also change the amount of vectors here. Since I've only time and that, maybe I want to let's keep it simple. Let's get rid of this, and the only data should be for at the moment the output itself. Let's have this, and we have the p-type controller still. There we go. Now let's open up a, a script here. Now what I want to do is I want to have a file name first of all. And this file name here is model2, the name of the Simulink model. Now before I also start everything, I might want to create the data I want to use. So basically, let's have a time of 10 seconds and a sampling time of 0.1. And let's have a reference signal here that is just once, and I will use the size of t, and let's say run model. Now I want to create this sim_in, since this will be used for the simulation. It comes from the workspace. I should place these as rows and as columns. So I will create that and run this. The size t reference. Oh, this should be reference and t. So basically, I have created sim_in now. Maybe I should try to run this here. Error, that's all dimensions. So it basically recognizes it, so I don't use that, I just use this here. If I run this, you can see that we are done. So this means that I should have a new thing that is called out here, which comes from the Simulink. I didn't have that, so I did the simulation here. So now I have out here. So basically, let's look at the structure of out. And I can see that if I'm using out point t out, I will get the time. If I use out point sim out, it will have something like time series. Let's try that, sim out. And I can now also see that now I can reach time here. It has time data, and the data itself is hidden here. So maybe I should use this st now, and then data using data, and then let's look what the data looks like. Now, since I've done that, maybe copy and paste, and I can see that this is data now, and it has just values in it. Maybe I want to use this here in order to have a I'm not allowed to do this basically. Now it's not finding that. So first I should run this part here, and then I should run the simulation. With this one, model 2. Exactly, let's save. Let's run this. Once I'm done, I can go ahead and run this here. And I can see now I have this nice structure here. So, but I will not basically go ahead and do it this way, because I have a pre-code and then a post-code here, and then the simulation is done here. It would be nice if I had some way of simulating stuff. So let's come to that. So basically, I can use something called a function called load system here. So it will load the model, and therefore I will provide it the file name. Now, if I give the file name and create this object here, I can use this object in order to set some parameters here. And these parameters are also accessible using the Simulink file here. But I will not use anything here, because I can just go ahead and just run it. I don't need to set any parameters. If I can load the system, if I can say somehow run the Simulink model, that will be enough, because I have ready stuff in my workspace here. So I did load the system. I have the simulation input that is necessary for the system. Now I can go ahead and use the sim function, and I will give it the file name, and it will be basically done. But after that, I might also want to, once I have the data, I might want to save the system. So I can say save system, MDL, the model, and I might also want to close the system, because I did open it up. So I don't want to see any window here. I might want to get the data, and that's it. Now if I run this, sim out time. So let's look at the workspace here. We have the answer, which is the simulation output. Basically, I have to do something like this, I guess. Let's say temp here. Let's look what temp has in it, because it might give me the outputs. I'm not really sure. Now if I run this in my command window, now I can see, instead of sim out, I have this I have saved sim out into this temp here, so I have to add temp dot here. Instead of out dot, I will use temp dot sim out and temp dot data here. That's an important difference here. Therefore, I might go ahead and look for T, and let's run this. Now you can see I have this 10 seconds, 10-second array of time, or I might also have the data. So you can see that I have the data. Now, this it can help out where for complex things it might help out because keep in mind that it does the simulation for me. So if I change it to 2 times once, I will see that there will be a result that is calculated. Now, this is not using the workspace variable that is already used or generated by the simulations before or the previous simulations, but it will just go ahead and tell the Simulink, tell Matlab to run the Simulink file in behind the scenes and then get me the data. So let me just come here and since I'm not saving it to the mat file, I can just go ahead and use this plot here. So it is possible to generate a plot. Since I've used here, I've loaded the data, I can now create a figure. And maybe maybe we should manipulate it so that we have the same structure as this one here, at least for the first one. Since I have the data, I might want to paste it here. This is not necessary, but time, reference, disturbance, noise, and output should be here. So let's get rid of this PI for them at the moment. And then this here. I keep in mind that I should open up the I messed up. I should open up the where is it again? The model here. There we go. Maybe we should also open up model in order to copy and paste stuff. Now I can see that I have the same structure here. So I will get rid of this here and this here. So let's get rid of that. I might want to copy everything that is in here. I should copy it like this. And then the sim in should be here, the sim out should be here. I might also want to copy the subsystem. Now you can see the advantage in using a subsystem for the reference because it will generate automatically and I will not keep track of what's happening there or what did I miss here. It's just a bundle that helps me out. Now I can also go ahead and connect this here. I only need the reference as an input and I have the disturbance and noise generated in here. Maybe I should get rid of this reference here because that's not necessary anymore in this new subsystem here. So basically I have a disturbance, a noise that is fixed, but my reference comes from the simulation workspace and it will apply it to the control system. So basically I don't need this reference anymore because I will provide it. So this means that I don't have to save it. I might change it to 3 and the first one should be disturbance here and the second one should be noise here and the output can be the last one here. Let's get rid of this. Let's connect it back here. So I have to adapt my code for this. If I save that and if I close this here, let's go ahead and adapt our thing. So we have reference, we don't have to define it back. So I'm not sure if the first one is time anymore. Let's get rid of that too. Let's look for it's a time series. So maybe that should be an array now. Let's say okay and don't bother with that. The first one, the second one, the third one, but it might be different. I'm not really sure. You'll see now. Now that we have any error here, so you cannot use docs. If I try to use this here, look for the workspace, and we see that this is basically Simin is a double of two signals. A double of two signals. Let's click here. We have a double of two signals. Alt signal. Interesting. Oh, this is sim in. We don't have sim out. We have temp, which is a simulation output. So if I look for temp or even temp dot sim out, temp dot sim out, I can see that it has three columns. So there's no time data involved at all. But this is column wise. So maybe I should get rid of this here. Let's try this out. Nothing makes sense. Um, the symout itself is the data, so basically I should get rid of the dot data here. And let's try it again. Temp temp.symout is a thing, and I should be using that, and I'm doing it. So what's the problem here? Maybe time. Time is the issue here, because I have to use directly T-out, temp.T-out. So these structures need a little bit parsing, or you might want to read or try out information. So using array might be the best idea, or you might want to prefer the time series one. It depends on your choice. Let's look for disturbance now. So it's basically a signal. Let's look for a reference. Some interesting stuff is happening. Why do we have disturbance like that? Probably I should place this and try it again and look for disturbance again. Maybe we call it data. Yeah, let's see what data looks like. So first row all columns, second row all columns, and this should basically work. Let's see, we have 401 elements, and our time needs a little adjustment here. And my reference is a little bit different than the other one because my time changed, I guess. 401 elements here. Let's look for this size, or maybe we can use the workspace here. Reference is different than the other ones here. So it might be a good idea to still use the inputs or provide the inputs as outputs in order to not mess around or not keep track of the sizes here. So let's change it back to default. So it is a little bit a pain in order to accomplish what I'm trying to do. But once you've done it, then you will just go ahead and use it over and over again. So basically, this will pay off, even if it doesn't seem like that. It will pay off because you will be able to change the disturbance, the noise from the simulation environment and get an output to the simulation environment. So basically, you will not use the Simulink and you will not see Simulink. You will just design your system, the structure of the system, and then forget about it and use it for different inputs and outputs. Now, basically, I have now the reference too. So basically, I should define the first one as reference, second data, the third one, and the fourth one, and it should hopefully this time. You can see that the window closed that was behind the editor, because I have set a closed system. So once you're done with the simulation, you can go ahead and stop it. Now, this might not seem that important, and you might say that this is too much work here. I will quickly show you a modification of this code, and you will see what I mean by this code, or why I even bothered to generate this code here. Now you can see disturbance and that as I want it to be. Now I might want to adapt the code so that I can also give it the disturbance and noise from my workspace, and I will generate it on my own. Maybe noise is not a good idea to generate as a single, since it will be too much work for now, but you can do that. I'm trying to demonstrate it only, so let's try to change it so that I'm changing the disturbance from the output. So that will make more sense basically. So my simulation input is the reference, and it should be also the noise here. So I mean disturbance here. So basically, let's get rid of this disturbance, and since the block doesn't have anything other than the noise here, maybe we should get rid of it and put this noise generation here somewhere. And let's use a demux here in order to separate the signals that are that doesn't have only one size here, which have multiple data in it. So let's connect it as shown. Let's take it here. So I will basically use the I will get rid of disturbance, or maybe I can just go ahead and try something like this here. So it will um, be looking as simple as it was. So the thing will be that I will provide an array by simin, so that the second row is disturbance, the first row is the reference, and then I will let's say apply this to the system, and I need the reference back. So I have disturbance, so maybe the reference should be kept track of. Let's save it. Let's close it. Basically, the only change that I should do is I should put in my disturbance here, and my disturbance should be the same as reference, but this time I will have a point to gain for now. And if this will work, I will again, and you can see now I have given a disturbance here. It doesn't have the effect that it had before. Maybe I want to see that effect, so I can simply generate an array that will look a little bit different. Now I need a zeros and ones combination here, and I will use one comma length, and I will give it a time vector so that it should wait for 5 seconds. So I will calculate the length of this time vector and use that instead of counting myself. So this is also a nice idea. So I can use 5 plus 0.1, which is the next sample, and my stopping point is Tn. So basically, I have generated a step function. So if I run this, you can see now I have a sort of a step function here. I have changed it so that it is a step function, and then since this was the P controller, I should be seeing the effects. Let's make a little adjustment here. I want to disable the noise so I can focus on focus on my disturbance here. Goes to disturbance, and there you go for disturbance. Maybe I will be able to show. Now I can see now, since I have high gain, I can see now that my system has a slight response here, and I might want to look here, and it's my controller, and I have 50. Maybe we should change it so that I have only 10, to see a little bit better. Now there's a nice effect. Now I can just go ahead and try something different. Maybe we want to see the effect of this, let's say, value of the disturbance. It might be something else, or I might want to change the controller parameter. I will come to that in a moment. But if I want to see this value here, I might want to create or recreate it over and over again. So therefore, there are some possibilities, but I will use the simplest one. Let's say for I equals, uh, let's say, or let's say gain equals 0.2, 0.4. Just two samples here. And I will go ahead and um, let's do not plot anything else than the output that I'm considering here. So maybe we should have this. And before I save and close anything, I should just go ahead and plot here. And the display name should be the disturbance gained. So let's say gain. Let's have this here. And it should be gain. And num to str should change it. There we go. Once I'm done, I should be having this. So having the result here. So we did have an error, and I did a typo, and then the dimensions concatenated are not consistent. So, this should be redefined every time I'm trying some stuff, because I'm changing t and then it messes up stuff here. So 0.2 and 0.4 disturbance gain. Let's say, I guess I forgot to change this here. So now I should see the effect, and I can see that they have a different values here, different responses here. So basically, what I've done here is that I have shown you to use a Simulink model, and I'm using the code in order to generate a different plot. Now, it would have not be possible to, it was not possible to use Simulink that easily in order to generate, let's say, a plot that will be generated now, because I'm basically changing the values, and it's not that easy to generate this plot, because maybe I should disable this show here. Let's close this in order to have a better transition name. You can see that this was not that easy with Simulink, because you have to run it so many times in order to get this here. You can see the envelope of disturbance response here, and you can see the lower and upper bound 1.8 something around 0.9 or 0.85, something like that is lower bound. So you can observe this. Maybe it's not a good idea to change the disturbance, but maybe the effect of gain is a better idea. So therefore, that's also possible. You can change everything that you can change here via code, so it's basically not that hard. I'm going to cut this. I'm going to paste it here. I'm going to cut this. I'm going to move it there. So I will connect it directly. So, and I will show you how to change this. Now I should give it a name. So let's give it KP. So this name is very important because I will use that name in order to access the value of this. So how can I do that? Well, and I will have a different gain, let's say 1 and 3, so 3 values. My disturbance should be always 0.2, so I'm not interested in that. I will still see the response, but the thing that I will change is that before I start, I should change my gain value. Therefore, after I have loaded the system and created a figure, I might want to, let's by the way, tap one tab here. So I might want to change the parameters. So therefore, I have shown you set param here. And using the set param, I should provide it the model name, and then I should use the name in order to access that. I said that this is KP, and I guess it should be called value here, and this value is basically num to str gain. Now let's run, and hopefully we will not crash, and we did. So wrong number for input arguments detected. Num to str, this here. So what's the problem here? Maybe I should. Oh, it is the gain, I guess. Gain of gain. I'm not sure. Let me click there. Now, if I double click this, I have this gain. So basically, it should be gain. Let's say help set param, but the help is not that helpful most of the time. But I can see it here. My model 0. Oh, I get it done. This should be concatenated. So these are not different parameters. It is like this here, and then it should basically work. But invalid symbol object name not found. Interesting. Because it is file name, I guess. MDL is not that. So it is file name slash kp. Is it? Exactly. Okay, now you can see that I have changed the k values here. And if you want to see the values that you've used, you can just easily go ahead and say this was kp, and then just let it show again. Now I can see that if I use kp1, I have this response. So it has basically a better, it has a, it is the worst case scenario for these 3 values. And the best one is this yellow one, because this yellowish one, because it has a better reference value or output value, lesser steady state error, because this distance is not that big, and it also has a little effect, or it has less effect for the system. And I can now, let's do not show the legend here. Now I can go up to 100 and see what happens. So what I do here is using this for loop, I'm basically uh, running the simulation file, Simulink file, 100 times. So there are 100 simulations carried out. And keep in mind that by clicking the Simulink model, it's not really that possible. You might generate this via only code, but if you have some complex models, then it will also be a pain to convert these models, those connections into code. That's also not that simple. So to use both of them suiting your need is the best that we can do. Now you can see that it becomes faster. There are some numerical errors, but you can see that we have we do speed up, and the effect of the storms becomes less and less important as k increases. Now we have seen that we can use a Simulink block, so that Simulink model even, so that we can code a wrapper that uses the Simulink model in the background and it generates our results. We can use the workspace for interchanging variables. We can use files, and it is also possible to just use files and use a mux, dmux to arrange it so that we can access all the data via code. But it is also a good idea to use the sim function, which simulates this Simulink file, because it's not really that difficult to adjust stuff. You can just make static changes by double clicking the model, and you can do the dynamic changes via code. So I can change the gain, and we can repeat this for all controllers or different structures. So basically, it is a good idea to code and generate code and use Simulink together. So that's that basically. Let's generate a better graphic here. You can do all sorts of stuff. Another important thing that I lastly want to show you is that I might want to use a Matlab function, and let's create another model. And if you have this here, and let's, for example, let's have a sine wave. I can have a sine wave, I guess. That's not what I'm looking for. Sometimes the library browser is better, sometimes typing is better. It depends on your needs. The signal for the sources, there we go. These sources should be helpful. And if I have a sine wave, there we go. Now let's have a sine wave, and let's also have a additional user-defined functions. Let's use a interpreted Matlab function. I guess that was it. Might be a Matlab function, but let's try the interpreted one. And let's have a scope again. So I want to keep it simple. Scope. There we go. Now I want to code this, and I want to use apps. So I guess it should work. I'm not really sure anymore. So if I run this and double click this scope, you can see now this is the absolute value of sine. So basically anything that can be interpreted by Matlab, you can type it in here. Or you might also prefer a different version of Matlab function that can be, of course, this Matlab function, which has an input and an output. Basically, this is a function that we can use via code, or that we generate by coding. So this is just a function. If we double click it, we will have this function here, and we can now do some crazy mathematical stuff or MATLAB stuff. Let me get rid of the first one. The first one is an interpreted function, which means that it will run on the fly. So if I type in something in this command window, it will be the same here. So it's basically accessing the command window and doing it that way. But the other one, the Matlab function here, if you remember, if I click start or run here, it has a slight compiling process in the beginning. So this function will be compiled quickly, so as other functions also are. So this is a more general version. And you can see that this is only a one-line function and the input and output is provided by default. If you don't want to have a one-line interpreted function, you most probably want to use this one. So I can just go ahead and do some crazy stuff. I can do the same. I can take the absolute value of the input and reflect that into the output. You don't need to save anything here. You can just go ahead and close, because if you double click it, it will be still there. So this is a function stored in the model, so you don't save it anywhere in the workspace. You can see that compiling did take a little bit more time. For some reason it takes too much, but let's get rid of this. But hopefully it will, and you can see that it parses, it compiles the Matlab function, and then it initializes and runs it. So it's a little bit different than the other one. The other one was on the fly. It gives the same result if you code the same thing, basically. So, but this can be a multi-line complex function that is an algorithm of you, a filter that you've designed. It depends on that. Maybe you like to use this here. Now, let me tell you about an issue with this method. This method cannot use any memory. So basically, if you want to have a global variable, let's say if you want to uh, have a causal filter, or if you want to something that you can calculate here, it's not possible to directly define something here and do that. Maybe therefore, you should maybe go ahead and use some memory blocks. And we can see them somewhere here. I guess this was exactly. So in order to do stuff that has memory in Simulink, that, for example, uses the samples that were used in this Simulink. So I have to define a data store memory, and I can read and write to it. So that's basically it. So I have to change the inputs and outputs, their definitions. This will change the structure of the block, and you will see it in a minute. So let's say mem out, and this is basically mem in, so memory in, and this is memory out. If I close this, not save it, and come to the model here, you will see now I have memory in and memory out, basically. So I have to, there will be one read and there will also be a write. So if I want to write to the memory, I am going to connect this one. If I am going to read, I will connect to this one. If you change A, the variable name, this is sort of a tag, so basically you can change that, but in this case I won't change it. Now I can do something like this. I have an output to provide, maybe the absolute value, or I can bypass that and I can just pass it here, but I might want to use this memory in, not int, by the way, memory in, and I might say mem out should be mem in the absolute value of the memory, or basically not that, but the absolute value of the input, plus absu, and this way you are actually taking the absolute value and the integral of this. It's sort of the integral. Basically, you take the sum of this. So maybe this is something you might want to do. And let's run this here and see what happens. Maybe I need also a display in order to see the value. Hope my Matlab will respond here. Basically, my there we go. Let's use this. Now, this mem out was in order to write it, and this mem in was in order to read it. So I should read the data into my display. Let's run this for 10 seconds. And I can see that I have added some data to it. I might also want to attach a scope in order to see how this data changes. Maybe I want to do that. Let's run this. If I click the scope, I can see now it is a periodic summation of the absolute values. I can see that this is the first period, and I'm adding together the whole thing. And if I don't take the absolute value, I might also divide by 10, so it will give me some area calculations, or I might look for the time and use that time. So if I'm not mistaken, there was something called clock, and this clock was giving you the time measurement. So you can use this as an input to your function. Let's try that out. Let's say time. I'm always hitting save, I don't know why. So I have a time input. If I connect this there and double click this function and use time times this here, and get rid of ops and just take the integral here, close that. So run this, and it should be it gives me something like this here. And let's look at the sum. Kind of gets out of control, I guess. What was the time? It should be giving me time. Let's see if it is time. It is a ramp function that shows me the time exactly. So I am calculating time. I have the data here. So I'm adding time view. So I'm adding the value calculated with time. Oh, okay. Maybe I need the sample time here. So therefore I need to use this here. Now it is 0.2. So maybe I might want to use 0.2 here. Close this, and there we go. It shows me now a different value here, and let's see what the value is. There we go. I can see that it changes here, and basically this is the positive value that changes. Now if I divide through time, I might get something that gives me a certain gain. I'm not sure, but it might give me the time that since I have 10 seconds, I should divide by that, and it gives me 0.18, etc., etc. What I mean by this is you need to use this memory storage thing here in order to have a function that can use memory, and you should use data write and data, or memory write and memory read. Therefore, I did memory in, memory out, whatever you will call it. You can also keep track of time, and you can get the input and output. So if you have a certain algorithm that should be applied, it is easy to use this method here. By the way, last but not least, I should talk about the solver information stuff here. You have certain settings about Simulink, and this is used for the ODE solver in the background. You can say there it should be determined automatically by the solver, or I might want to pass in my argument here. So if you go ahead and to fix that, it might be a good idea. You can then use one of these here, maybe OD4 for cutoff, or there are also other methods implemented, the Hoyne method, the Euler method, etc. And you might also give it a sample time. Let's say 0.01 is nice, so we can do that. Let's apply, and it will be changed. It doesn't affect that much, but depending on your differential equation or your model, you might want to change other stuff. You have these, but it's not really that important. We did see how to solve this. Data types, diagnostics, hardware implementation. These are out of our scope most of the time because it is too advanced for basic users. So let's do model 3 and save that. Now if I run this, you can see that I have this here. You can increase the sampling time, but this may also cause some performance issues, so keep that in mind. And that's basically it. So I have shown you how to code so that we are using Simulink in the background, which is the best idea if you have some cases to try out, if you have multiple simulations in your mind. You should use a helper code or a wrapper code that carries out the simulation stuff in the background. If not, and if you're just designing one controller with certain little things, then that might be a drawback because you are coding everything. That might be not that ideal. If you just want to try out something on the fly, go ahead and use Simulink on its own. You can include Matlab functions. You can use this, and as far as I remember, you can also code your function externally and use the interpreted function so that you give the name and it will use that function automatically. So you have to little bit use the MathWorks help and documentation interfaces in order to learn this, and the more you use, the better you will get at Simulink. But using this video as a reference for advanced application might help you out, and this is also the aim of our today. This was also the aim of today's lecture. So hope that it was helpful, and see you in the upcoming lectures.